Hello, algebra students. Welcome to virtual GED class. We're on lesson 8 of Algebra Essentials. We're going to up our game in the world of multiplication so we can handle some more challenging examples. We're going to start multiplying with some groupings. So before we even launch into what distribution means in the world of math, let's relate it to just basic English. It's a common enough word if we say distribute. So if I say to you to distribute something or distribution, Miss Annette, what would you think of?
Giving out money.
Absolutely, giving out or passing out. I could say to you, if you were in my class, would you please distribute these papers to the rest of the class? You'd be passing those papers out. That's the idea here. Distribution is the idea that multiplication can pass out. Now, what does it pass out to? That's the key we need to take away. Multiplication can pass out to every term. And that's a math word that just means things that are adding or subtracting in a grouping. Basically, what I'm saying here is that if you have a number that is multiplying with a group that involves addition, subtraction. So there's things adding and subtracting in your grouping. For example, x squared plus 4. Usually when we look at something like this, we would go, oh, hey, there's more than one thing to do. I should hit up the order of operations. There's multiplication here, but there's also addition here. The order of operations would tell us to tackle the grouping first. Come here and look at this grouping. X squared plus 4. Back when we talked about combining like terms, we said you can only add if you have the same kinds of things. I don't have like terms here. This is an x squared term and a constant term. I can't add. So does that mean we walk away? There's nothing we can do here because we can't do the first step? No. Distribution says even if you can't add, you can still pass out the multiplication. You can multiply the x squared by 6 and the 4 by 6. In this case, and don't worry, we'll get into it deeper, but you would get 6 times x squared is 6x squared, and 6 times positive 4 or plus 4 is positive 24 or plus 24. So that's the kind of math we're going to be doing today. We'll see lots of examples from simple to complex. We'll learn a lot about why it works this way. I'm going to try to prove it to you. You know how I am, Miss Annette.
Should we always use Gemma when we see this type of problem?
Well, that's the thing. I wanted to use Gemma, but I couldn't. I wanted to do the grouping first, but I couldn't. Is it hopeless? Is there nothing I can do? Because basically this idea of like terms kind of thwarted me from using Gemma. Well, no. What we're going to learn today is that you still could distribute because they give you the same answer. Distribution works too. It's kind of like when you want to go to the store the usual way, but there's a detour. So you say, oh, okay, well, I'll just turn right at the next turn. And then I know if I go past the 7-Eleven and take another right, then I'll get back to the store the back way. So that's the idea of distribution. When the Gemma road is closed for you, there's another way you could still deal with the multiplication. So the first thing I would like to try to prove is that distribution makes sense. So what does this say, first of all? Notice how the 3 is shoved up against this parentheses, this whole grouping. And there's a lot going on in this group. So what this says is that entire group is happening 3 times. Now I'll just read the example. It does say 3 times the quantity of, and again, I'm saying quantity to signal that the 3 is multiplying the whole group. So 3 times the quantity of 2x squared plus 4x plus 1. Let's think about this by definition. What am I saying? I'm saying that this whole group is happening 3 times. So let's start with the group. 2x squared. What does that mean? Well, it means I have an x squared and another x squared plus 4 x's. Okay, I can do 4 x's. 1, 2, 3, 4 x's. And I have a 1. But I don't just have that once. I have that whole group 3 times. And so I'm not just going to write that once. I'm going to write that line exactly the way I saw it, a total of 3 times. There is a visualization of 3 times 2x squared plus 4x plus 1.
Would we have to do that each time?
We're going to be lazy and we're going to be fast. We're going to use distribution to do this the short way. But before we start applying the short way over and over again, I need to prove to you that it's not just some random rule to memorize because mathematicians invented all these rules to torture you. This is the way it would really work if I really had X's and I really had X squareds, or I really had oranges, this is how life works. And so, of course, it's how math works. It's that idea of math is not rules to memorize, it's patterns to notice. So I'm asking you to notice a pattern. So if I were to write all this stuff out, which I won't because I'm super lazy, but we're just going to do it the one time or maybe twice or three times. You know how I am. But after that, we'll do it the lazy way a lot, I promise. So now let's examine just the X squareds. How many X squareds do I have now after writing out these 3 rows?
6.
6, exactly. I have 2, 4, 6 X squareds. And plus I have some X's. How many X's do I have?
We've got 3 rows of X's.
And each row has?
4.
So I have
12.
exactly 4, 8, 12 X's. And then I have some ones. I have 3
3
ones.
ones.
So I'm just adding in, like adding in 3 $1 bills, I'd have $3. So I have 6 X squareds, and I have 12 X's, and I have 3. And that's what that statement down there says.
I'm looking at 3 times 2, which would be 6x. 3 times 4 would be 12x. 3 times 1 is 3. Okay, I got it.
Brilliant. Exactly what I wanted you to see. The lazy way. Yes, you can write it all out like this, but dear goodness, how much time do you think we have? We could just multiply. If I have 2x squared happening 3 times, you're right. I'm going to have a total of 6x squared. But it's not just the 2x squareds repeating. It's everything. So I'll also have the 4x happening 3 times, 12x's. And I'll also have the +1 or the +1 happening 3 times. And so I'll also have +3. So we looked at the visual representation, but what I would also like to point out to you is you have been distributing since you learned multi-digit multiplication. Our work looked different, but my argument is that you used the very same process of passing out. So if I were going to do 3 times 241 by hand, the common way that we teach in school is to take 241, to put 3 right down there, and then do this process. And this process is interesting. And that's what I want to point out to you today. Because what would you do from there? You would say, well, I will take 3 times 1. And you'd say 3. But you weren't done with the 3 yet. It's not like addition and subtraction where we only do it in rows, right? You kept on passing out, didn't you? The next thing you would say is, I'm going to now do the 3 times that 4 that's in the tens place. So really you were doing 3 times 40, but you never thought of it that way. You just thought of it as 3 times 4. And you said, okay, well, that's 12. And you put the 2 and you put the 1. And then you still weren't done with the 3. You weren't done with that 3 until you passed it out to every single digit in the first number. You would then do 3 times 2, which of course is our 6, and add in that 1 you carried and get 7. So you would take the 3 and you would multiply it by some number of 1s. And then you would take the 3 and multiply it by some number of 10s. And then you would take the 3 and multiply it by some number of hundreds. You were passing it out, each piece of your number. Now, sometimes you'll see on some math worksheets them asking you to do things like this, where instead of using the traditional process, they want you to look at 241 not as a single number, but as 3 numbers, 200 and 40 and 1. That's what this says. Now, the reason why they did that is not to torture you, or not because they think this way of multiplying is faster. It's because this way is easier for mental math. If you break it up into pieces, you can still pass it out just like we did, but you can organize the numbers better in your head. Because I'm going to do 3 times 200. I'll just end up with 6 hundreds. And I could do 3 times 40, or 3 times 4 tens, 12 tens, or 120. And then I could do 3 times 1. And of course, we know 3 times 1 is just 3. Now, this is easier to juggle in my head than trying to keep track of all these numbers and this carrying and having this mental picture in my head, because now I can just put 600, 120, and 3 together. And of course, I would get 723 if I did it this way as well. So either way I do it, whether it's this mental math strategy I did second, or the traditional multiplication algorithm I did first, I'm organizing the work differently. I'm writing it down differently, but I'm doing the same work. I'm passing that 3 out to every piece of 241. Okay, well, that's exactly what we're doing. It's just not hundreds and tens and ones. It's x squareds and x's and ones. 3 times 2x squared, just like 3 times 200 was 600, 3 times 2x squared is 6x squareds. And just like 3 times 4 tens was 12 tens, 3 times 4 x's is 12 x's. And then, of course, it doesn't matter if I'm in arithmetic or I'm in algebra. 3 times 1 has always been and will always be 3 ones. And I want you to look here because I would argue that algebra is easier than arithmetic. You know why I say that? Because you're done. Back up here, we had 600s and 12 tens and some ones, and we had to do some more work. We had to do the addition, didn't we? But here we don't have to. We have 6x squareds and we have 12 x's and we have 3 ones, and we get to go home and drink tea because there's nothing else we could do here. We couldn't do the addition if we wanted to. I'm done now.
We're done. And I would have been that one of those students that would try to figure out, now what do I do?
Now, what do I do? How do I crunch them together? And
Yes.
I always joke that you guys are my B students. I love you so much. Okay. I'm not making fun of you when I say that because you guys are wonderful, hardworking students who do well because you earn it. And you guys see those plus signs and you say, Kate wants me to add. And you just take that like so personally that I cannot stop my day until I have added for Kate. And I do appreciate your dedication, but you can't add. So no one to go home, drink your tea. It'll be fine. Now, I've been talking about we can pass out that multiplication across addition and subtraction. So I'm going to show you something you may never have noticed. Let's look at this first example, 7 times 29. We're going to do just like we did before. We're going to use that algorithm, that step-by-step process that teachers generally teach for multiplying on paper. So I would start with doing 7 times 9. So 9 times 7 is 63. And if you don't know that multiplication fact, that is not the point. I don't want you to stress out. But then I'm not done now, right? I got to keep passing out that 7. So 7 times 2 is 14. Adding in that 6, I get 15, 16, 17, 18, 19, and 20. 203. So now, if I wanted to do 7 times 29 mentally, I would never try to do this. I'm not trying to remember 9 times 7 and keep track of carrying. It would just be gross. It would be gross. So if I wanted to do it mentally, I would probably use this little subtraction trick I have right next door. First, I have to prove to you that it's the same math. So do you agree with me, Miss Annette, that 29 is the same as 1 less than 30?
Yes.
Okay, wonderful. Well, if 29 is the same as 1 less than 30, then 7 times 29 should be the same as 7 times 1 less than 30. Interesting. They should come out to the same answer if those two things are really equivalent. And we can see that they will. Take a look. 7 30s or 7 times 30 would be 21 10s or 210. But then from that, I could just take away the 7 ones. That would be a much easier way to do this problem if I wanted to do it mentally. 209, 8, 7, 6, 5, 4, 3, 203. Now, again, this is not an argument. Oh my gosh, people like to fight with me online. Please do not write me a lengthy comment about how Common Core math and new math are stupid and the old way has always worked and we don't need a new way and this is slow and dumb and you hate me. That's not my point. My point is whichever way you prefer to multiply, whether I do 29 times 7 or I do 7 times 30 minus 1, I am passing out that 7 to some groups. Okay, so now I want to compare the 7 times 1 less than 30 or 7 times the quantity of 30 minus 1 to 7 times 1 less than 3K. That's what that says. 7 times the quantity of 3K minus 1. Instead of having 3 tens, this time I have 3 Ks. But same basic idea, pass that out. If I have 3 Ks 7 times, I have a total of 21 Ks. And no matter if I'm doing arithmetic or I'm doing algebra, if I subtract 1 7 times, I will have subtracted a total of 7. Or another way to think of it is -1 times 7 is -7. And again, I would argue that algebra is easier than arithmetic because I am Done. It's finished. Whereas in arithmetic, I could do 21 tens minus 7. And so I had to keep working. I had to count down. There were fingers involved.
Okay.
So same exact process. Multiplication has passed out from the very first time we tried to apply it to a 2-digit number, and it's going to pass out till the end of time. If you have numbers that are adding or subtracting, like 29 is 20 plus 9, then your multiplication passes out. Let's do some
Oh.
examples. And now, no more pictures, no more fruit, no more explanations. I might explain a little bit. You know, I can't help myself, but let's just multiply. So first of all, I
Wow.
want to read this. This says simplify 9 times the quantity of. See how I'm opening up these parentheses and there's more than one thing adding and subtracting in there?
Yes.
That's why I say times the quantity of. 9 times the quantity of r cubed minus 14. Now, I want to ask you a couple of weird questions so that if and when you get lost in the symbols, when you're multiplying, you know how to get yourself unstuck. So look inside this grouping for me. How many terms are in here? How many numbers are adding or subtracting? Well, we have an r cubed, and then we have this minus 14. We could also call that a negative 14. So this sucker has 2 terms, 2 things that are adding and subtracting. Adding or subtracting, you know, we talked about that. The line kind of blurs once we get to negative numbers. That means that we'll have 2 acts of multiplication, just like when we had a 2-digit number. So let's do it. Let's pass that 9 out twice. First, we'll pass the 9 out to r cubed. And what is 9 times r cubed?
9r cubed.
Exactly. It's just 9r cubed. You just shove the 9 up against the r cubed to say, hey, they're multiplying. Now, as you multiply, I want you to read that as negative 14. Not because it's not minus 14, just because your calculator's little stupid. Your calculator doesn't know that minusing 14 is the same as negative 14. Like, I owe you $14. We're going to take $14 out of my money. But we need to be able to type this into our calculator. We can't type 9 times minus 14. It'll give us an error. But we can type 9 times negative 14.
Negative 126.
Beautiful. Or minus 126. I see still this operation of subtraction here, Annette. So we have to ask ourselves, can I do this subtraction?
I think we're done.
We're done. Exactly. There's an r cubed term and then there's a constant term. And so again, constants are just, they have no letters on them. They have no variables. We can't combine those. And so, yeah, we're done. Where it will throw students is when we start getting variables involved. There's more than one p or more than one x or x's and y's all over the place. We start glitching a little bit because those symbols are confusing. But do remember when we have repeats, see how we have a p and another p?
Yes.
When we multiply with repeats, we use exponents. And that's the only way this one gets a little trickier. So we're going to take 4p and we're going to multiply it by the first term in the parentheses. Annette, what's the first term in this parentheses?
6p.
Good. Multiplying 4p times 6p, we know that we can deal with our coefficients, our numbers first. So 4 times 6 is
24.
24. And then we know that we have some factors of p multiplying. So we'll put a p, and then we'll use exponents to tell us how many factors of p we have. So how many p's are multiplying?
2.
2. So we'll have 24p squared. Now I'm going to take 4p, and again, yes, that says minus 3, but right now I'm multiplying. So I'm going to do 4p times negative 3. And again, you don't need to be great at negatives or even great at multiplication. You can feel free to do that in your calculator, but you won't be able to do the p. You'll just have to do 4 times negative 3. So 4 times negative 3 is?
Negative 12.
Wonderful. Then it's up to you to know we've also got a p.
Oh, you have the p there too?
Yes, on some other examples, I was passing out or multiplying by just a plain old number, but this time I was multiplying by 4p. So that p is going to make its way into every single term. Okay, now take a look at this expression that I have. 24p squared minus 12p. Can I do this subtraction? Are those terms like?
No.
No, so I'm done. Fairly simple to multiply in algebra. The trick is to remember that multiplication passes out and that we use exponents for repeated factors. So this might look a little uglier. I have a negative here, tried to scare you with this. And this time I have how many terms in my grouping?
You have 1, 2, 3 terms.
Exactly, I have 3 terms. So it's just like when I take a 3-digit number and I multiply by something. I'm going to multiply by -7 3 times. So let's start with -7 times 8n squared. Again, use your calculator for the coefficients, for the numbers. What is -7 times 8?
-56.
Wonderful. And -56 what?
N squared.
Exactly.
But can I ask a question? When we're ready to distribute -7 and you go to -n, would I be putting a 1 there?
Yes, brilliant. That's exactly why I made the problem like this. If you
Okay.
don't see a number out front, it's a 1. So that is -7 times -1n. So even if you are struggling with negatives and you're not great with them, you could still do -7 times -1 in your calculator. Nice. Which would give me what?
7.
7. We are multiplying 3 times. We have these 3 terms. Just like after you do all your multiplication, you add up everything you have under there. Same thing here. We're going to see plus 7n because it's a positive 7n.
Ah,
And now we're going to do -7 times +6. What is -7 times +6?
-42.
So we're going to write -42. When we're multiplying, we call it negative. And when we're adding, subtracting, we say plus and minus, but same basic idea. And now we need to look at this. We have 3 terms in our answer, so we should ask ourselves, can we combine any of these terms?
No.
Oh, we're done. Nice. I
Yes.
like simple. All right, beginners, we got the basics of distribution down. Go ahead, stop this video and go tackle your practice. Remember, there's always Mathability guided practice for you if you feel like you need a little extra support right now. For my experience level students, I know what you're thinking. Give me something good. Well, here you go. Turns out subtracting polynomials, yes, that's right, I said subtracting, is an application of this distribution. Well, why? Let's take a look. It says subtract the polynomials, and these 2 things within the parentheses are polynomials. And basically all that is a list of terms. So this first one is a list of terms, 9x squared minus 3x minus 4. I have 3 terms. And from that, I'm going to subtract another list of terms, x squared plus 2x minus 6. Now, yes, this is a subtraction example, but like we talked about on the last example, when you just have a minus in front of a variable, we said it's like you have -1 of that variable. The same is true with parentheses. When you just have a negative outside of a grouping or a minus outside of a grouping, it's like you have -1. You're minusing 1 of that grouping. And so what I'm going to do is shove a 1 up in here. And in order to drop those parentheses, I can't just drop them because the parentheses tell me right now that this whole group is subtracting. And so I am going to need to distribute the subtraction. I'm going to need to pass it out. And again, you can think of it as multiplying everything by -1. -1 times x squared is just -x squared or -1x squared, same thing. -1 times +2x, well, -1 times +2 is -2, and there's an x multiplying with that, I just shove it up against there. And then -1 times -6 is +6. A negative times a negative is a positive. And so everything in that grouping that was adding turns into subtracting, and everything that was subtracting turns into adding. Now, how about the first grouping? This one doesn't have anything out front. See that? And so I can just drop this grouping, these parentheses, without it making a difference. And now that the parentheses are all gone, you can see, yes, this is 2 separate polynomials, but it's basically just a list of terms. Now we have 6 terms, and we can go ahead and combine like terms. So starting with the x squared terms, I have 9x squared there. And I'm going to take away an x squared, and remember it's 1x squared. So 9x squared minus 1x squared is 8x squared. Notice I'm adding, subtracting now. My variable portion doesn't change. I don't see a change in the exponents. Now I have some x terms. I have a -3x and a -2x. And again, you can do the coefficients in your calculator. -3 minus 2 is -5. And what was I adding and subtracting? X's. And now finally, I have a -4 plus 6, that will give me a +2. And again, look at these. The terms aren't like. I have an x squared term, I have an x term, and I have a constant term. I'm done. Nice.
Ooh.
Don't panic. Same skill, calculator handles ugly. So let's look at example 5. Now, first of all, Miss Annette, what is it asking me to do or to find here?
I don't know. We're just solving it, I guess.
Yeah, that's all I'm looking for. It's not some trick question. They're asking me to solve. A lot of times students will think, well, solving and simplifying, they're two different worlds, so I'm not going to use this skill. Why are you talking about distributing when now I'm solving equations, Kate? Why'd you just flip into a new world? But what we learned before is that when we're solving equations, an equation is an expression equal to another expression. And we see that here, right? We have a expression, a simple one. It's just a plain old number, but equal to another expression. And we've talked about this before, but we said if you can simplify one or both of those expressions before you start solving, you should. And I do see some simplification I can do on the right-hand side. I see in this particular equation, not all equations, but in this particular equation, that I have a number, 3/4, multiplying with a grouping. And so before I even start solving, I could just perform that multiplication. I could distribute that 3/4 out in order to make this sucker a little simpler. And by the way, this is one of the GED test's favorite style of equations. They like to throw a fraction at you with distribution to see if they can freak you out. But you say, I'm not scared of fractions.
I'm not scared of fractions.
Yeah, I'm multiplying my calculator. Somebody just yelled at me on YouTube a couple days ago. Not everybody has a calculator. And I was like, you should go buy one. I didn't even engage. No engaging, Annette.
Okay, I got my baby. I take her everywhere with me.
Strong work. I'm like, we only have so much time. Do you want to spend 27 years with me, or would you like to just spend 19 bucks, buy your dang calculator so you can go to college? Invite me to your college graduation. I'll clap for you. Okay. So let's do that. We're going to take 3/4 and we'll multiply it by the first term over here. And again, you can do it in your calculator. What is 3/4 times 16?
That gives me a positive 12.
Beautiful. And so I'll get 12. 12 what? Well, it's
12y.
Exactly. Now, 16y wasn't the only term in this grouping. I also had minus 28, or when I'm multiplying, I read it as negative 28. So why don't you go ahead and do 3/4 times negative 28 for me?
That gives me a negative 21.
Negative 21. And now I just made the expression on the right-hand side of my equation a little simpler. Is that legal? Yeah, sure it is. You can trade out anything that's equal in math. That's equal and simpler. So that's my new right-hand side. On my left-hand side, there's no simplifying I can do. And wow, did distribution help me to make this nasty equation look a whole lot nicer?
So that's done. There's nothing more to do.
There's no more simplifying to do. It's not
No
going
more
to get any
simplifying.
simpler. You're right. If I just look at the right-hand side, Annette, nothing more to do. And if I just look at the left-hand side, there's nothing more I can do. So my simplifying is done, but I still haven't solved. This time I have the equal sign. So I have the equation. So I have the power to solve. On those other examples we've been doing, numbers 1 through 4, we didn't have another side. We didn't have an equal sign. All we had was an expression to simplify. So once we combined it, that was all we could do. But now that I have this equal sign, I can solve. Now that I've done all the simplifying I can do, I can start working backwards, moving things around across the equal sign to solve. So in order to solve this equation, I need to get rid of two numbers. There's a 12 hanging out with y, and then there's this minus 21 or negative 21. Now, we learned when we were solving that we would work the order of operations backwards. So we should move anything adding or subtracting first. We'll move the 21 since it's subtracting. Now we're solving.
Yes.
Now we're moving across equal signs. Now's the time to be disobedient. Back when we were simplifying, we said, okay, it says multiply, I'll multiply. Now we've ran out of things we can do forwards. We've ran out of obedience that we can do. And so now it's time to be disobedient. We're not going to subtract 21. We're going to do just the opposite. We're like teenagers once we hit algebra. We're going to add 21. Now we can do whatever we want as long as we do it to both sides.
The other side.
That's what makes it legal to use opposites, right? I have another side. Those last 4 problems, I didn't have another side, so I had to stop. So now let's take a look at what happens. Subtracting 21 and adding 21 cancel. I've got 12y, and there's the math to do, 39 plus 21.
And that gives us 60.
Good. And now I am not done yet. No, I can't do 12 times y, but I sure do have an equation, so I sure can solve for y by getting rid of that 12. How can I get rid of that 12?
Division.
Beautiful. I'll divide by 12. I can do that because there's another side. Hop across that equal sign, do the same thing over there. Multiplying and dividing by 12 cancel their opposites. I have y alone just like I wanted, and 60 divided by 12 is
5.
beautiful. So the thing I want to point out today, not that distribution has to be part of solving equations, but it can show up. So if you can make things simpler in your equation by distributing before you start solving, by all means, go ahead, do it. Another thing I want to point out to you is that if we understand what we're writing means, we can also use this idea to help us write expressions, equations, and inequalities. I'm not talking about doing distribution. I'm talking about what it means when we have a number shoved up against a grouping. Let me show you what I mean. So example 6 says, write an equation that could be used to find b, the base of a parallelogram, with a height that is 4 centimeters less than its base and an area of 77 centimeters. Now, if we were just writing this from scratch, it would be more challenging, but I love that we have some multiple choices so we can try to narrow this down. But the first thing I want to do is, they talked about area, base, and height of a parallelogram. That sounds so formula sheety to me. As soon as you see language like that with these geometry measurements, go to your formula sheet. Okay, we don't have to try to do this by memorization. That's not the point of the GED test. They give you those formulas so you don't have to memorize, so you can focus your brain power on the mathematical reasoning. So go hit up the formula sheet for me. I need a formula that relates base, height, and area of a parallelogram.
That's area equal base height.
Good. Area equals, and you said base height because they're shoved together. What are they doing if they're shoved together, the B and the H?
They are multiplying.
They are multiplying. Okay, so this says to find the area, multiply together the base and the height. Okay, let's go looking in this problem for what we know about area, base, and the height. So let's start with area. Go read that problem for me. Is the area known? Do we know what the area is, Miss Annette?
Yes, it's 77.
Beautiful. So A is 77. So on one side of the equal sign, I should have 77. And I see that they're all equal to 77. Equal to 77. That's nice. Okay. That part's checking out on all of them. Now, on the other side of that equal sign, though, we have equal to base times height. So go take a look at this word problem. What do we know about the base?
We don't have anything, no number.
Exactly. We don't know the base, right?
We
We've been
don't
told to
know.
find it. Well, in algebra, when we don't know something and we've been told to find it, we use a variable. They told us what variable to use. What variable do they want us to use?
The B.
B. All right. We'll just keep calling B B. It's been working for us so far. Now, the base is supposed to be multiplying by the height. Go looking through this problem. What do we know about the height?
It's 4.
It's not 4, but it involves 4. Make sure you really closely read everything we know about the height.
Oh, 4 centimeters less than the base.
Exactly. The height is 4 centimeters less than its base. That's not a 4. Like a lot of students just want to write 4, but it's not a 4. 4 centimeters less than something could change a lot based on how big that thing is, right? It varies. Let me say that again. It varies based on the base. So what they're saying is, if you want to have the height, you got to take the base and have 4 centimeters less than that. And take a look at that. Look at D. D says take the base and then multiply it by this group, 4 centimeters less than the base. This whole thing is the height. Now, why did I choose that one and not the other ones? They all look really similar. They all have minuses. They all have 4s. But I want to look at A and C first. Notice that the base is not multiplying with the whole height on A and C. Let me show you what I mean. On A, the base is just multiplying by 4. See the parentheses stop?
Yes.
We said our height was 4 less than the base. It's that whole thing. So we're not going to multiply by just 4 and then subtract the base when we're done. Same thing with C. C says, well, multiply the base times just the base. We need to multiply the base by the whole height expression. So that just leaves us with these two. These two are groupings. Now, with we've applied the concept of distribution already. That's how it applied to this by narrowing it down to B and D. Both of them have base multiplying with this whole expression. So what makes them better or worse than each other? So whenever you're getting lost in symbols, I want you to look for differences, not similarities. So look at B and D. How are those two different?
Problem B, it says 4 negative B. And then on D, it says B negative 4. So,
Yeah,
but I
it's
would,
order. That's what's different, right? It's order. In the first one, we have 4 and we're taking away B. In the next one, we have B and we're taking away
4.
4. So
Wow.
this is not about distribution. This is about language. A lot of students, if I just say 4 less than B, they want to say 4 less B. But that's not how life works. Miss Annette, if I said that you are 4 inches less than I am, you wouldn't say 4 and take away my height, or else then I'm saying you're negative so many inches tall. Like that makes no sense. You would take my height and you would take away 4. So same thing here. I wouldn't say, oh, I'm going to take 4 and take away B. I'm going to say, oh, if I want 4 less than B, 4 less than the base, that's the base, take away 4. That's just how we write it. And so this says, take the base and multiply it by the height. The height is 4 less than the base. And so that's why we have this B times B minus 4. All right, tricky.
That's tricky.
Yeah, but it'll be multiple choice on the GED too. So even if you could have crossed off the two that weren't a grouping, you know, oh, that one's not a grouping, that one's not a grouping, you'd have a 50-50 shot of guessing which one's the right one. So let's look at example 7. So the language here is interesting because it's something I haven't taught you, but I want to help you figure this out by looking at the answers. So first, let's read the question. It says factor 24y squared minus 48y minus 44. Now we've talked about the word factor, but we've talked about it like it's a noun, a factor. I keep talking about factors as things multiplying. But this is not, I'm not using this as a noun right now. It's something I'm telling you to do. I'm saying factor. I'm giving you a verb, an action, factor this thing. I'm giving you instructions, but they're related. I'm still telling you something about multiplying. To factor something is to do almost the opposite of multiplying. It's to pull something back out into a multiplication problem. To factor it is to say, what numbers multiplied? What factors made this? Now, if I was going to teach you to factor 24y squared minus 48y minus 44, we would take weeks in our class to learn all the different types of factoring. However, that's not what we're going to do today. It's a useful skill. Don't get me wrong. You need it for college. But today we're going to cheat. Yay, guys, letting you cheat by looking at the answers. I want you to look at these answers and what they look like.
Ooh.
Notice that they look like numbers shoved up against groupings. They're multiplication problems. The problems are the answers, and the answers are the problems. Factoring is working backwards, taking what you guys would think of as the answer and turning it back into the problem. Well, if you don't like that working backwards, you don't know how to do it, we can go straight to the answers and work forwards. Let me show you what I mean. So instead of factoring this out, I'm going to do the opposite of factoring, and I'm going to multiply. Let's check A. So if I were going to multiply this out, 6 times 4y squared is what?
That's 24y squared.
Good. Let's write it right up here so we can compare it. And now 6 times negative 8y.
That gives us a negative 48y.
Beautiful. And now 6 times negative 7 or minus 7.
That will give us a negative 42.
Shoot, close, but no cigar. We matched our 24y squared. We matched our negative 48y, but instead of having a negative 44, we had a negative 42. A does not work. Let's keep guessing and checking. What would you like to guess now?
Well, the obvious choice is C.
All right. Let's give it a try. Let's multiply out C. So first, let's do this first act of multiplication. 4 times 6y squared is?
24y squared.
Brilliant. That one matches. How
C.
about 4 times negative 12y?
Hey, that gives me negative 48.
We like that. Negative 48y. It's looking good so far. Last act of multiplication. 4 times negative 7.
Negative 28, and that's wrong too.
Dang it. Looks so good. I had this one student who told me, Kate, I don't really need to do any of this for the GED. The answer's always C. I was like, that's why you're in GED class and not at your high school graduation right now. The answer is not always C. All right, what's your next guess?
B.
B.
Number
All right, let's do it.
6 times 4 is 24 y squared.
Good.
And then, of course, our next one is negative 48y.
Brilliant.
And then, uh-oh,
Uh-oh, what you see coming, girl?
oh, that ain't right either. The next one, 6 times negative 11, negative 66. That's not it.
That's not it either. And you know, it might be frustrating for you to guess and check wrong, but I like it because it means we get to practice 4 times. Not gonna lie. It's the math teacher in me. All right. It must be D, huh? Let's make sure that Kate doesn't have only wrong answers like she sometimes does. 4 times 6y squared is
24y squared.
good. 4 times negative 12y is
Well, that's negative 48y.
good. Our first 2 terms have been working out this whole time. How about our last term? 4 times negative 11 is
Of course, it's negative 44.
hallelujah, finally.
Lord have mercy.
All right, he had mercy. He had it right there at D. And I was just listening to a sermon about how trials refine us. Look at us just getting refined, Miss
Yes,
Annette.
Lord. Mm.
Consider it pure joy. One of the things the GED sometimes asks you to do is find errors when students are solving equations. And that can be tricky to do because there's often different ways to solve an equation. Like we could go different routes, and as long as we both do true things, we're going to come to the same place. Well, when you're evaluating someone else's work, you don't only have to know your right way, you have to know kind of all the right ways so you can find the wrong thing they did. So let's take a look. It says a student's solution to an equation is shown below. What common error did the student make? Now, if you feel like when you're looking at this, you get lost in the symbols, don't feel bad, so do I. Even as a math teacher, I can get lost in the symbols. So I highly recommend that you go on the side and try to do the problem yourself and see if I do what they did, what would I get? So I'm going to start by just writing this same equation down over here, negative 6 times 3x minus 7. Look how that 3x minus 7 is in parentheses. It's negative 6 times that whole grouping of 3x minus 7 equals 48. Now, if I were going to do this, there's a couple of things I can do. You know, I can start solving right away, trying to get rid of numbers, or we can do like we did last time, Miss Annette, which is simplify before we solve. Take a look at that left-hand side. Do you see any straightforward math you know how to do? Can you obey any of those symbols?
Well, we can distribute.
Bingo. We could distribute the negative 6 through to the 2 terms in there. Let's do it. What is negative 6 times 3x?
That gives me negative 18x.
Good. Now take a look over at their work. We have negative 18x.
Yeah.
They have negative 18x. I like that. Let's keep going. What is negative 6 times negative 7?
Positive 42.
Positive 42. Brilliant. Or plus 42. And right away, I can see the common error that this student made. And it was definitely during their distribution, wasn't it? They got a negative 18x. I got a negative 18x. I have an equals 48 and they have an equals 48. But they have a minus 42.
Negative 42.
And so what common error did this student make? They just made a sign error when distributing. And I really don't care how you write this. When they do it on the GED, they just tell you in what step did they make an error. So you don't have to give words to it. You could just say, oh, it was the first step. Right from the beginning, the student struggled.
But what if you had went to x equal negative 5? How
Yeah,
would we have
that
known?
line, I would just keep going. They're not showing you their balanced change. So they're not showing you that the first thing that they did was distribute, and then they got that. They're not showing you that the next thing they did was add 42 to both sides, and they got that. They're not showing you that the next thing they did was dividing on both sides, and they got that. So you would have to go do your work and then compare the next line. Do your work and then compare the next line. So that way that I force you to show me your balance change on both sides, a lot of mathematicians get lazy. They stop showing you what they did. They just do it. But unfortunately, when you're a newbie student, if you skip showing me what you did, you guys do nonsense. You do crazy, crazy stuff. So I always make you show me on both sides. Whereas when you go to college, your teachers will not. They'll just like jump and you'll be like, how are you jumping? They're doing their balance change without telling it to you. So let's look at example 9, advanced. It says simplified, and we have something interesting going on. It's not multiplication this time. This time I have a big ugly grouping, but instead of the whole thing being in parentheses, this whole big ugly grouping has a fraction bar under it. What operation is it when I see a fraction bar?
Division.
Division. So this whole big ugly number happens to be called a polynomial because it has those multiple terms. But this whole big ugly thing is being divided by -8. Now, multiplication and division are inverses. So that being said, if multiplication passes out, guess what? So does division. I don't want to bring up anybody's elementary school trauma. So trigger warning. You could just go ahead, pause me for a second or go curl up in the fetal position. But we did this when we did long division. We passed it out. We said, how many times does the 5 go into the 3? How many times does the 5 go into the 8? How many times does the 5 go into the 5? Now, there was more work than that, and I'm not going to make you do it because I'm aware of long division trauma. However, it's the same idea. It passes out. And so we can do that here as well. We can say this -8 is dividing all 3 of these terms. So we can divide this first term by -8, and this second term by -8, and this third term by -8. So let's start here. Let's do -48c squared, the first term divided by -8.
6.
Exactly, c squared. Gorgeous. And I can keep on passing it out just like I used to in long division when I wasn't crying. So what is 32 divided by -8?
That gives me a -4c.
Brilliant. And we can keep going. What is -40 divided by -8?
Oh, +5?
It is. And so I'm going to write that as +5. If multiplication passes out to every term in the grouping, division can do the same. And yes, we've done that since the beginning of math. Let me do a simpler example. So how about 2 into 486? It's easier to see here because 2 goes perfectly into 4, doesn't it? 2. And 2 goes perfectly into 8, doesn't it? And 2 goes perfectly into 6, doesn't it? So even though we didn't organize our work the same way, we did the same thing. We passed out that 2 to every digit.
Oh,
We're passing out that -8 to every term.
God, I love how you explain things. It just works.
Well, I need you to understand we're not doing something new. You guys think we're doing something new. I'm like, we're doing the same thing. Example 10. What is the simplified area of a triangle with a base of b centimeters and a height of 5 centimeters less than twice its base length, or 2b minus 5? Okay, don't panic. Look at the language. What is the simplified area of a triangle with a base? Sounds formula sheetish to me. Don't cry until you look at your formula sheet. When I was a high school math teacher, I gave my students a point just for writing down the formula. They could have no idea what to do with it, but I'm like, thank you for finding it. 1 point. So hit up your formula sheet. What formula relates the area, base, and height of a triangle?
That is area equal 1/2 base and height, which are multiplying.
Good. 1/2 times base times height. Now, just like always, we can plug in what we know, whether we know numbers or we know weird variable facts. Okay, let's take a look. So first thing I see is, what is the simplified area? Area is the thing we're finding. It's a mystery. A will stay A. That's not new. And equals stays equals, and 1/2 stays 1/2. None of that is new. We're cool with that. Now here's where things get a little funky. I don't have a number for the base, right? They don't tell us what the base is, but they do tell us they want us to call the base something. Look what they say. They say with a base of b centimeters. They're saying, well, keep calling the base b. Okay, I could do that. And then they said, and a height of 5 centimeters less than twice its base length. Okay, they're not calling the height h, are they?
No.
They're giving us information about the height, 5 centimeters less than twice its base length. Now, if you were doing this in your college class, they would stop right there, and you would have to figure out how to write 5 centimeters less than twice its base length in the language of algebra. But I was real nice to you. I wrote it for you. Or 5 centimeters less than twice its base length. That's what it says. 5 centimeters less than, you took 5 away from, twice its base length. That is the height. Yes, I could call it h, but I can also call it 5 centimeters less than twice base length because they mean the same thing. And so I'm going to multiply 1/2 times b times 2b minus 5. Now, if I want to multiply b by that entire 2b minus 5, guess what I need? Parentheses. That says take 1/2 and multiply it by b, and then multiply it by that entire thing, that 5 centimeters less than twice the base length, the height. Now, I'm going to go ahead and do this simplifying now. You can see that, no, there's nothing to do on the left-hand side, but on the right-hand side, I can distribute 1/2 b to this sucker. So let's start with distributing 1/2 b to the first term in the parentheses. What is the first term in the parentheses?
2b.
Exactly. So what is 1/2 b times 2b? Well, I mean, you could type it in your calculator 1/2 times 2, but I like halving. Halving is easy. What's half of 2?
1.
Is 1. So I just have 1. 1 what? Well, I have b times b, or 2 b's multiplying. And so we said we'll write that as b squared. Now, this is true, 1b squared, but we're so lazy. We know we never write a coefficient of 1. So I'm just going to call that b squared. Lovely. Now, I passed out the 1/2 b to the 2b. Now it's time to pass it out to the -5. So you can do that one in your calculator if you'd like. But 1/2 times -5 is -5 halves. And then I wasn't just multiplying with 1/2, I was multiplying with 1/2 b. So I get -5 halves b. And now I cannot do anything else. Notice what they asked me. What is the simplified area? They didn't say solve for b. They just said, what is the simplified area? Well, the area is this. And I cannot simplify it any further because those aren't like terms. I'm done. That's the simplified area. Example 11. During their afternoon happy hour, Smenchie's Smoothies offers $2 off each smoothie for customers who pay in cash. Look at that language. If they take $2 off your price, what did they just do with 2?
Minus.
They minus $2. Good. There's going to be something about minusing $2, I bet. They took $2 away from the smoothie price. Felicity wants to treat herself and 4 coworkers to smoothies. She has $35 cash. Which inequality could be used to find P, the price per smoothie, before the discount that Felicity can purchase? Now, you guys have a tendency to do the math and write about it later. Mathematicians write the whole thing out in our language, and then we do the math, translating it first. And so that's what we have here. We have this translation of the cost of a smoothie. They're saying the cost of a smoothie, how we figure out our cost, better be less than or equal to $35. And every single one of those says that. It says something is going to be less than or equal to $35. Something is going to be less than or equal to 35. Something is going to be less than or equal to 35. Something is going to be less than or equal to 35. So in all of these, I'm going in there, I'm Felicity, I only have $35. I know my smoothies better cost less than $35. So we got some math glitch going on. We understand the back half of all of these, but we don't understand the front half. And that's where the differences are anyway. Remember, I said focus on the differences, not the similarities. They all say less than 35. But how they tried to find the cost of the smoothie differed. So first of all, I say that we can rule out 2 of these, Annette. Because you told me if they're taking $2 off, they're going to do what with $2?
Minus.
Minus it. So I better take off the one where they added on my $2. That teased me off. They're not going to add $2 onto my order. If they tried to do that, you'd be mad. You'd be like, that $2 is supposed to come off, not go on. Now I just have to decide if I'm multiplying 5 by this entire group. See the parentheses around P minus 2 there? Or
Yes.
what's the difference? Am I just multiplying 5 by P, the price, and then taking off the $2? So is the $2 coming off once, or is the $2 coming off every single time? We can go into the store and we could have a $2 coupon. Then we would buy 5 smoothies and we would take off $2. That would be this case. Or we could go to the store and we could save $2 on every smoothie. That would be this case. I'd take $2 off a smoothie and then I buy 5 of them. 5 of that whole thing. So go looking in my problem. I need some clues. Am I taking $2 off just the one time? Do I just have like a $2 coupon, or am I taking $2 off of every smoothie price?
You're taking $2 off of every smoothie.
Absolutely. And that is why I would choose B over D. So again, I'm speaking in my language, not your language. So let me show why that says that. This says take $2 off the cost of a smoothie, and then take that answer, that price you got, and we're going to pay that 5 times.
Oh, okay. I would have chosen D, but okay.
A lot of students would. But what D says is take 5 times only the price, and then just take off $2 once. You're not saving $2 on every smoothie. You just have a little coupon. Okay,
Yeah.
cool. So B is the correct answer. Nice. I want to reassure you, and I want to reassure Miss Annette that I know we did some challenging things today, especially for those of you guys who tracked with me into the advanced level practice. We were not playing. We were getting into the hardest problems on the GED, stuff that you don't actually have to answer to pass, but if you want a high score, then you would want to be able to get through to that math. But it's also college prep math. So yeah, we hit this concept at a high level, but the struggle is the learning, you guys. And so Kim has this great quote I love: struggling in mathematics is not the enemy any more than sweating in basketball. I dare you to go tell a basketball player who's sweating that he's not good at basketball. Why do we tell a student who's struggling that they're not good at math? It's a clear sign that you are in the game. It's the ones who are sweating who are doing the best job out there on the court. Fair enough. You struggling in math class? Thank you for thinking hard. You are a mathematician. So how do you get to the point where it's not such a struggle anymore and you don't sweat so much anymore? Well, guys, you get stronger. How do you get stronger? Sorry about that. You got to go to the gym of math. The gym of math is the practice. So guys, go hit up the gym, pick your level of practice. If you are still struggling and you wanted to about kill me when I tried experience in advanced level practices, then Mathability is where you should be at, guys. Get more of the guided practice. But otherwise, hit up the level of practice most appropriate to you, beginning, experienced, or advanced. And again, don't stress yourself out if you're at a beginning level. That's fine. If you are just starting out in basketball, I'm not going to throw you on the court with, I don't even know any cool basketball player names. You have to help me out, Annette, with
LeBron.
LeBron. Okay. I'm still on Magic Johnson. It's been a minute. Well, I'm not going to throw you out there with them, okay, until you get a little practice. So don't try to hit up the advanced level. Don't try to jump in an NBA game before you learn to dribble. So pick your level of practice, tackle it. Make sure you spend more time practicing than you spend listening to me. Just like if you want to play basketball, you got to spend more time dribbling than you do watching the game on your couch with Doritos. All right, fair enough. Super proud of you guys. Did hard work for me today. Y'all are amazing. Don't you feel amazing? See you next time. Happy learning.